Hey everyone, this is the third lecture, Lecture C from Chapter 17. And we're going to talk about intensity of sound waves. Basically, this applies to all waves as well. But we'll also talk about the sound level, which is unique to sound waves, although it could be used for other waves. But we usually talk in terms of decibels, or what we call sound level, for only sound waves. So let's go ahead and share the screen here. And we'll go ahead and talk about intensity first and define that. But you can see this is the third lecture, Lecture C of the Chapter 17 and part of Chapter 33 module. So let's define intensity. So intensity is power over area, right? So, or P over A. Now, remember that power is work or energy over time. So plugging that in, we find that intensity is the energy in a wave divided by the area per second, right? So every second, it's how much energy is falling on a certain area. And the units of that are watts per meter squared in the metric system. Over here on the right, I have approximate intensities for various situations. So, for example, a jet plane, when you're 30 meters away, is 100 watts per about 100 watts per meter squared, which is a very high intensity, which would cause you extreme pain. Going down just to a normal conversation, we see that there's a humongous difference in the number, right? We're going from 100 down to 10 to the negative 6 watts per meter squared. That's a very big difference, about 8 powers of 10 or 8 orders of magnitude. And this is one of the things about what happens when we use intensity in watts per meter squared is that there's a huge variation in the numbers. And so what people have done is they introduce a new scale, decibels, which we're going to talk about here later on in the lecture. But you can see the variation in this scale is not nearly as big as in the actual intensity scale. For example, the jet plane is 140 decibels, normal conversation is only 60. Now notice that that's a difference of about 80 decibels. So maybe you can see the correlation. 10 decibels corresponds to a power of 10 in the intensity. A power, if I go up by 10 decibels, I'm going to go up by a power of 10 in the actual intensity in watts per meter squared. And this will be a property that we can use logarithms for. And we'll see that here in a moment. The next thing I want to talk about, apart from the definition of intensity, are a couple of things. First of all, I want to talk about how the intensity is related to the amplitude, right? So by amplitude, I mean either the displacement amplitude or the pressure difference amplitude that we've talked about previously. And I'm not going to prove this equation. It is derived in the textbook. Maybe later I'll make a video that derives all of this stuff. But the main thing I want to point out here is that the intensity of a sound wave is proportional to the square of the amplitude. It also depends on the density, the wave speed, and the frequency. But as far as the energy goes, it's proportional to the square of the amplitude, which if you remember a spring, a mass on a spring, the energy there was also proportional to the amplitude, the square of the amplitude. And this is true for any wave, any type of oscillation. Intensity is proportional to the square of the amplitude. So going on here, I want to look at a particular situation, and that situation is of a point source. What I mean by a point source is it's like a single point, and it's emitting sound or energy in all directions equally, or sometimes people call that isotropically, right? So it's going out in all directions, kind of like a light bulb would emit light in all directions equally. Well, as you might guess, the intensity or the loudness of the sound is going to get weaker the further away you get. And the reason for that is that the sound wave is going out in a spherical way, and the area that's covered by that sphere gets bigger and bigger, the bigger the radius of the sphere. So the further away you get from the sound, the energy has got to spread over a much larger area, and that weakens the intensity. And intensity is what we hear as loudness. right? It's directly related to how loud we hear a sound. And the main point is that for a point source at a distance r, the intensity goes as power over 4 pi r squared, where r is the distance from the source. And where does the 4 pi r squared come from? Well, maybe you can see it's the area of that sphere that all the energy is now spread around. Again, that area is getting bigger and bigger. So here's just again a definition of intensity: power over area. Power is energy over time, and power or intensity goes as proportional to the square of the amplitude. All right, so the point source, we'll remember that formula for the example problem I'm going to do. Now, we've defined intensity in watts per meter squared, but there's that problem of it's got a huge variation, and many powers of 10. Going from normal conversation to the jet engine is 8 powers of 10. That we don't want to deal with that. We'd like to deal with a smaller range of numbers, and since we notice they change by powers of 10, that makes it perfect for logarithms. So before I define what a decibel is, let's just review some properties of logarithms. Remember that, typically you're probably more used to the natural logarithm. When we talk about decibels, we're using a power of base 10 logarithm. So when I say y equals log of x, it's the same as x equals 10 to the y, right? So the way you would notice that, or kind of reverse this, is if you take the logarithm of x, it's equal to the logarithm of 10 to the y. But what a logarithm does is just pull down that power of 10, right? So the y is just equal to the logarithm of x. It's telling me the power of 10 of that number. And I have a few examples here, right? Log of 100 is the same as log of 10 to the 2. So the logarithm is 2. Log of 10 to the 5 is 5. Now you can have negative numbers if you have negative powers of 10. Log of 0.001 is 10 to the negative 3. Log of 10 to the negative 3, and that logarithm is just negative 3. Okay. You can also do operations with logarithms. This is convenient when you're multiplying numbers, because I could take the logarithm, for example, of a times b. It's just equal to log of a plus log of b. Now, if I take the divisor, or the divide a by b and take the logarithm, it's log a minus b, or minus log b. And now another convenient thing, of course, log of a number to the b power. This is actually wrong. This should be b log a here. The point is that it's going to pull down that power and just make the logarithm of the base number there. So here are some other examples you can look at that apply those formulas. I have one this class that will use them tremendously, but they're good to just review here in case you do come across them again. So now that we've talked about logarithms, let's go to the definition of sound level and decibels. So sound level is related to the ratio of the intensity to a reference intensity. And so we got to choose a reference, right? And we're going to figure out how many powers of 10 our sound that we're hearing are compared to that reference. Our reference intensity is going to be what we call the threshold of hearing. So it's roughly about where you would be able to just barely start hearing a sound. And that number is defined to be 10 to the negative 12 watts per meter squared. So I'm going to define my decibel level, this beta, my sound level in decibels, as 10 decibels times the log of the ratio of the intensity I want to determine the decibel level for, divided by my reference threshold of hearing intensity. Since it's 10 to the negative 12, right, I could just multiply by 10 to the 12. So it's I times 10 to the 12 here. And as a couple of examples, the intensity of a baby crying is about 0.001, or 1 times 10 to the negative 3 watts per meter squared. So what is the sound level? Well, it's 10 to the negative 3 times 10 to the 12. That gives me a 10 to the 9 here. And logarithm of 10 to the 9 is 9. And then I multiply by the 10 decibels to give myself 90 decibels there. So hopefully you can see that it's pretty simple how it works. I just take the power of 10 down there. Another example is where sound waves is used a lot and decibels are important is in ultrasound. In medical imaging, using ultrasound, you don't want to make the intensity too high because it could have effects on the tissues of the person being examined. But 100 watt per meter squared intensity level, well, I've got log of 10 to the 2 times 10 to the 12. That's 10 to the 14. Logarithm of that is 14. Then I multiply by my 10, and I get 140 decibels. So that's pretty much it for the definition of decibels. There are cases where you may be given the decibels and you want to find the intensity. Maybe let's look at a case like that real quick. So let's say I wanted to go from 90 decibels to whatever the intensity is. Now we know the answer. It is going to be 10 to the negative 3 watts per meter squared. But how would I do that using this definition here? Well, what I could do is if I know I have 90 decibels, I'm going to take the log of this. Well, first of all, we'll take 90 decibels and divide by the 10. So I'm going to get 9 is the logarithm now of 10 to the of I times 10 to the 12. Now the question is, how do I get rid of the logarithm? So I'm going back to that definition. I'm just going to write 10 to the 9 and 10 to the log. So I basically put them in the exponent of a power of a base 10. And so 10 to the 9, the 10 to the log just gets rid of the logarithm. It's I times 10 to the 12. So now maybe you can see when I divide by 10 to the 12, I will get my intensity is 10 to the negative 3. And that would be in watts per meter squared. So this is just a quick example of kind of going the other way, right? Going from the decibel level to intensity. You could possibly come across both. So hopefully that's a good quick definition of decibels. Let me bring up the table again of intensities and sound level for different sources. Again, I want to point out that when you look at the decibel level, there is not as much of a variation in the number. It's easier to talk about decibels than saying 10 to the negative 2 or 10 to the negative 10 watts per meter squared. It's easier to say 100 decibels or 20 decibels, but they really correlate to the same thing, right? We're just using this logarithm to kind of translate back and forth between them. The other thing, again, to mention is notice that every time I go up by a power of 10, so when I go from 10 to the negative 11 watts per meter squared to 10 to the negative 10, I go from 10 to 20 decibels. Every power of 10 corresponds to 10 decibels. Okay. Just as a quick, pretty simple example, I think this is again a problem from the textbook. The source of a sound wave has a power of 1 microwatt. If it is a point source, what is the intensity 3 meters away? So let's do that. We know that a point source, the intensity goes as the power for 4 pi r squared. So this is just easy, right? It's 1 times 10 to the negative 6 watts, which is a microwatt. And then I'm going to multiply by 4 pi, or divide by 4 pi times 3 meters squared. And I end up getting for that 8.84 times 10 to the negative 9 watts per meter squared. So that's my intensity, my actual intensity. The question is, what is the sound level in part B? Well, that's our decibels. But just real quick before I do the calculation, let's guess. So this is about 8.8 times 10 to the negative 9. So looking, it's close to 10 to the negative 10. So it's going to be, well, I don't know, maybe it's actually a little closer to 10 to the negative 8, right? 8 times 10 to the 8. So it's probably somewhere close to 40 decibels, if that makes sense, because it's getting close to 10 to the negative 8. 8.8 times 10 to the negative 9 is pretty close to 10 to the negative 8 watts per meter squared. But in this case, right, I can't easily do it. I'm going to have to just use my decibels, 10 decibels, times the logarithm of my intensity, 8.84 times 10 to the negative 9 watts per meter squared, times the 10 to the 12 reference intensity. Now this is actually meters squared per watt, since I kind of inverted the number. But what that's going to do is give me a 10 to the negative 3 here. So 10 decibels log of 8.84 times, or not negative 3, 10 to the 3. And if you do plug that in your calculator using the logarithm key, you'll get 39.5 decibels, which is what we guessed. It's pretty close to 40 decibels.